So our first example with Coulomb's law is going to look at if we have a hydrogen atom, can we determine the size of the force that's acting between the proton in the nucleus and the electron that is orbiting within the cloud, right? So our basic Bohr's model of hydrogen, right? We have our proton here, and then around that proton we have an electron which orbits in some fashion. And what's the force? So these are opposite charges. So these are going to be an attractive force, an electrostatic force in between them, and again they are equal and opposite. So things that we know. We know our charges. The charge of the proton is going to be 1.6 times 10 to the negative 19 coulombs. That's just the fundamental charge, right? The charge of a single proton or a single electron. The charge of the electron is going to be negative 1.6 times 10 to the negative 19 coulombs. And we can look up this radial distance here. Which is 0.53 times 10 to the negative 10 meters. Okay, so we need all of our units to be in the SI units of meters, coulombs, and coulombs. All right, then we're just going to plug that in to our equation, our Coulomb's law, and we're going to be able to determine what the size of our force is. Remember, this is squared, okay? Common mistake that people make. We need to make sure we square that. Plugging that into my calculator, 9 times 10 to the 9, 1.6 times 10 to the negative 19. This is actually going to be squared, 1.6 times 1.6. And remember, this is actually the absolute value, so we really don't need to worry about one's positive and one's negative. (0.53 times 10 to the negative 10 squared. Okay. Plug all that in, and we're going to get a force of 8.2 times 10 to the negative 8 newtons. So our second example is if we have three charge objects, negative 8, and this is micro coulombs, 3 microcoulombs, and negative 4 microcoulombs, and they're stationary, can we find the net force acting on particle 3? Okay? So anytime we're working through examples, I always encourage you, if you want to pause the video, take a few minutes, see if you can figure it out on your own, and then go ahead and play the video to see myself work through the problem. That would be really a good practice of, okay, I see what there is, can I figure it out? If I can't, let's let Mr. Ellison work through it, and we'll see how he works through the problem, okay? So the first thing I'm going to do is I'm just going to label all the forces that are here, whether they're on particle 3 or not. These two forces are going to be attracting, they're opposite signs. So we're going to have the force on 1 due to 2. We're going to have the force on 2 due to 1. Those are attracting forces, they're equal and opposite. Okay? I'm going to have 1 and 3. Those are repelling forces. They're both negatively charged. However, I notice that they're pretty far away, so I'm going to try to draw my vectors appropriately. And so I'm going to draw this a little bit smaller. This is the force on 1 due to 3. This is the force on 1 due to 3. And then I have these two here. These are attracting, and they're closer. So I'm going to have the force on 2 due to 3 and the force on 3 due to 2. Right? Then, if I'm trying to find the net force on particle 3, what I can see is that these two forces are going to cancel each other out. So actually, F net of 3 is going to be F32, the value of that, minus the absolute value of F13, or 3,1. Okay? That's going to give me my absolute value of my net force, and then I can tell really I won't be able to tell the size of this until I know exactly which one's bigger, okay? So I'm going to plug each of those, and I'll just do the first one for you here. We'll do F32. K, Q3, Q2 over R squared. 9 times 10 to the 9. 3 is -4 times 10 to the -6 coulombs. Multiplied by 2, which is 3 times 10 to the -6 coulombs. Divided by 0.2, and that is squared, okay? When I plug that in, I get 2.7 newtons, okay? I'm going to do F31 as well. It's going to be the same thing. I'm just going to switch out my distance as well as my charge, this charge there. And when I do F31, I get 1.2 newtons, okay? So my net force then on charge 3 is going to be 1.5 newtons, and let's see, F32 is larger, right? So that's going to be to the left. Okay. So our last example is going to look at, if we take that same scenario, what if we added a fourth charge, right? So we're going to add Q4, and we're going to say that charge can either be positive or negative 10 microcoulombs, whichever one we really need. Where could we place that so that the actual net force on 3 is 0? Okay, so what we had currently was we had a net force of acting to the left of 1.5 newtons, and so what we really need is we need a force of 1.5 newtons acting to the right, because if we have that, then we have a net force of 0 because all my forces are going to balance out. So how can we do that, right? Well, let's think about that. There's really two ways that you could do it. One is if we were to place Q4 to the right, right? That would need to be an attracting force. Because this is negative, this would have to be a positive, okay? How else could we get another force acting of 1.5 newtons to the right? Well, we could put a negative charge, right, over to the left. We don't really know exactly where. If we put charge here and made it a negative, that's going to give me 1.5 newtons that way because they're going to try to be repelling, okay? So what we're trying to figure out is what is this distance? In either circumstance, that distance is going to be the same, whether it's to the left or to the right, to the left as a negative, to the right as a positive, because our equation is based upon the charge size, the magnitude of the charge size, not necessarily the sign, and the distance away from that charge, okay? So here's what we know. We know that the force needs to be 1.5 newtons, right? And we're trying to look for D, okay? Our equation, F equals K Q over R squared. Again, R or D is going to be replaceable as meaning the same thing, okay? I'm going to work through it, and this is a really good habit that we need to start getting into, is that the numbers really don't matter right now, right? What we need to do is we need to be able to manipulate this equation to find something that just says R equals, because that's what our final value is asking for, okay? So to do that, I'm going to get R squared off the bottom. So I'm going to multiply each side by R squared. Cancels my R squareds out there, and I get R squared times F equals K Q. Divide each side by F. So I get R squared equals K Q over F. And then lastly is I'm going to square root both sides. So I get R is equal to the square root of K charge over F. Okay. We could then apply this to any problem, right? We have specific numbers for this one, right? And if we were to do that, then we'd have 9 times 10 to the 9 multiplied by, we'll do 4 microcoulombs. We'll just do 10 microcoulombs divided by 1.5 newtons. We'll square root that. Then we get 0.49 meters. Okay? So either way, we could be 0.49 meters this way. If we had a positive charge, we could be 0.49 meters to the left if we had a negative charge. Either one of those is going to produce a 1.5 Newton force on charge 3, canceling out this additional 1.5 Newton force from charges 1 and 2, and so our net force on charge 3 would be 0.